start with this chapter, and then we will continue after the Easter holiday. This chapter is about binomial distribution and Poisson distribution. We saw the normal distribution. I showed you all the things, and here we have the main issue is about the binomial distribution and the Poisson distribution. And later on in this chapter, we have an example for the Weibull distribution. But this is not the main thing here. The main thing is the binomial and the Poisson distribution. To understand these examples about binomial and Poisson distribution, at first we need some basics. The basics start very simple. And I will only show you some basics which you need to understand the binomial and Poisson distribution later on. So we will start with some very easy examples, and you will see it will become more and more complicated, and it is very important to get the feeling for probability and converse probability. And this is what I would like to show you in some examples here related to the basics of probability. Only as a preparation to prepare these things which we will go on further with binomial and Poisson distribution. So at first we will start very simple with some sheets about dices. This is the dice. And now we can ask a question: what is the probability if an event occurs certainly? And what is the probability if an event occurs certainly not? This means in these following examples, the probability every time is the number of favorable cases divided by the number of possible cases. What does this mean? The probability for a number from 1 to 6. So you throw the dice, you will get, of course, you will get a number from 1 to 6. And to get a number from 1 to 6 with one throw, you throw the dice one time, then the probability is 100% that you get 1 eye to 6 eyes. The probability for a number of 7 is 0 because the maximum number on the dice is 6 eyes. There are two rules which are important for the following sheets. This is the addition rule and the multiplication rule. This is about the addition rule. The addition rule is the probability that an event A or an event B occurs. Or every time if an event A or an event B occurs, then you have to do an addition of the single probabilities. This is the single probability that an event A occurs, and this is the single probability that an event B occurs. And the probability that A or B occurs, this can be solved by the addition rule if you do an addition of the single probabilities. It's not possible that A and B occurs at the same time or in the same case. This means event A exclude event B. An example. Again, the dice example. The probability for throwing 3 eyes or 2 eyes in one throw. This is the probability the single probability to throw three eyes. It is 1 divided by 6. There are 6 possibilities. And one possibility is for throwing 3 eyes. So the probability for throwing 3 eyes is 1 to 6. And the probability for throwing 2 eyes in one throw is also 1 to 6. Now the probability to throw the 3 eyes or 2 eyes, it's the addition rule. This means a plus, the addition of the single probabilities. The result is 33%. So this is a very simple example. Here another example, also very simple. How is the probability to get 1 eye or 2 eyes or 5 eyes? Well, also very simple. The probability to get 1 eye is also here. The single probability is 1 to 6. To get 2 eyes, also 1 to 6. To get 5 eyes, also 1 to 6. And if the question is 1 eye or 2 eyes or 5 eyes, you have to do an addition. So here you have the plus between the single probabilities, and the result, of course, is 50%. All experiments with equal single probabilities, like you see here, 1 to 6, 1 to 6, 1 to 6, these are called Laplace experiments. Here you have a card game. Skat is very popular in Germany, I think also in over Europe. Skat has 32 cards, and the probability for getting an ace at one time, well, there are 4 aces in the game, in the card game. In total we have 32 cards, and there are 4 cards in this 32 cards, 4 aces. There is a clubs ace, a diamonds ace, ace of spades, and the hearts ace. So we have 4 cards, 4 ace cards in the game. For getting 1 ace at one time, the probability to get the clubs ace is 1 to 32. And if you take a card one time, the probability to get the diamonds ace, with one card, if you take one card, and the probability to get the diamonds ace is 1 to 32. This is the single probability to take the ace of spades in one time out of the 32 cards, and this is a single probability for the hearts ace. So if the question is what is the probability to get an ace at one time, you can get the clubs ace or the diamonds ace or the ace of spades or the heart ace. So every time a plus between the single probabilities, and this means a total probability of 12.5%. It is an OR conjunction, so every time it is an addition of single probabilities, additional rule. Well, there is another rule which is called multiplication rule, and the multiplication rule means the probability that an event A and an event B occurs. And this is the product. This single probability A times the single probability B. This is the total probability that A and B occurs at the same time. So, just also an example, you have 2 dices, and the probability of throwing for throwing two 6-eyes with the two dices at the same time. So in one throw, you throw it one time, you throw both dices one time, and the probability to get 6-eyes with the two dices in one throw at the same time, this is 1 to 6 times 1 to 6. So this is an example for the multiplication rule. 2.78% is the probability to get 2 6, 1 6 on the first dice and 1 on the second on the other dice. This means total probability here to get both, with both dices to get 6-eyes is 2.78%. Again, the discard game. You take two cards, at first one and then a second one. What is the probability to get at first, to get the Jack of clubs, and at second, the Jack of diamonds, without putting the first card back? This is the first here, the Jack of clubs, and this is the Jack of diamonds. Well, you have and. So you have the multiplication rule. The first single probability to get the Jack of clubs is 1 to 32. We have 32 cards in the game. And then, without putting the first card back, means there are only 31 cards remaining in the game. And the probability to get a Jack of diamonds, if you take the second card, is 1 to 31. And this is, in total, it is a probability of 0.1% to get at first the Jack of clubs and at the second time the Jack of diamonds. So it's a very low probability. But here it is an example for the end conjunction, of an application of the multiplication rule. Another example, a dice example. The probability to get an odd number of eyes. This means it can be 1 eye or 3 eyes or 5 eyes. So we have or additional rule. This means the additional rule and 1 dice and 1 throw. Here we have the probability. The question is, how is the probability to get 3 6-eyes with 3 dice is thrown at one time? And here the next question is, what is the probability to get exactly 1 6-eye if thrown 1 dice 6 times? Well, let's take a look at the solutions. The probability to get an odd number of eyes. This is 1 or 3 or 5. This means additional rule, 3 to 6. This means 50%. It is an example for the OR rule, for the addition rule. The probability to get 3 6-eyes with 3 dice is thrown at one time. For the first dice, you have this single probability to get 6 eyes. This is the second dice. The probability is also 1 to 6 to get a 6. And this is the third dice. So you throw all these 3 dices at one time, and the probability to get 3 6s, you must have a 6 with the first dice and with the second and with the third dice. This means a multiplication. So the total probability to get a 6 with all of the 3 dices is 0.46. 6%. Okay, now the last question, what is the probability to get exactly 1 6i if thrown one die 6 times? Exactly 1 6i if thrown one die 6 times. Well, you have 6 options because you throw it 6 times. The first option is that you get the 6i at the first throw. The probability for that is 1 to 6. Then you get 5 to 6 is a probability to get no 6 in the second throw, no 6 in the third throw, here in the fourth, fifth, sixth throw. So this is a multiplication of the probability to get 6 in the first row and no 6 in the other throws. This means multiplication rule. Here you have 0.067 to get a 6 in the first row. Here the same to get a 6 in the second row. Here to get a 6 in the third row, in the fourth, in the fifth, and the last in the sixth row. So every time you have a single probability, for every option you have a probability of 0.067. Now it can happen, it can be that you get option 1 or option B or option 2 or option 3 or option 4. It is every time or. It can only be that it is option 1 or option 2 and so on. So you have to do an addition of the single probabilities, and then the probability to get 1 6 in 6 throws is 40.2%. So this is an example for an application of the multiplication rule. In every option, you have the multiplication rule. And between these options, it can only be that it is option 1 or 2 or 3 or 4 or 5 or 6. It can only be one of them. So or is the conjunction between the single probabilities. So this is the reason here, because you need the addition rule in this case, and the result here is 40.2%. Okay. In addition, what is the probability to get minimum 1 6i if thrown one die 6 times? A minimum. Minimum 1 6i means 1 6i or 2 or 4, 3 or 4 or 5 or 6 6i's. So you throw one die 6 times, and the question is, what is the probability to get at least, so to get minimum 1 6i? In this case, it is better to calculate the reverse probability. The reverse probability means the probability to get no 6i's. The probability to get no 6i, if you throw 6 times the dice, is shown here. It's 33.5%. So the probability to get minimum 1 6i is the inverse probability or the converse probability, which is 66.5%. So in this example, it is much more clever to answer the question not directly, to answer the converse or the reverse probability, which is shown here, and then to answer the question. And the answer of the question the probability we get minimum 1/6i is 66.5%. But the calculation is much more easy if you calculate at first the reverse or the converse probability to get no 6i. And this is the thing which we need in the next examples, and also, of course, in the binomial and Poisson distribution examples further on. But this is what we will do after the vacation, after the holiday, after the Easter holiday. Okay, so far for today with you